Hello everyone, this is Sopan Chavan and today we are going to learn the criteria for Riemann integrability. In the last lecture we have seen the first criteria for the Riemann integrability, and in this lecture we will see the second criteria for this Riemann integrability. Friends, this is the second theorem and let's see the statement of this theorem. So the statement is, if a bounded function f on closed interval AB is Riemann integrable if and only if for any epsilon greater than 0 there exists a partition P of closed interval AB such that this UPF minus LPF is less than epsilon. So this is the statement. In this statement we have necessary and sufficient condition. So first we will take this f is to be Riemann integrable on closed interval AB, and we will prove the necessary condition for any epsilon greater than 0 there exists a partition P of closed interval AB such that the upper sum minus lower sum is less than epsilon, and conversely we will prove this function is Riemann integrable on closed interval AB by taking this upper sum minus lower sum less than epsilon. So let's see the proof. So in this proof, what is given data? Your given data is given that f is Riemann integrable closed interval AB. Okay, so this is the given data, and this means that this upper integration over a to b f of x dx is equal to the lower integration over a to b f of x dx, and which is equal to the integration over a to b f of x dx, right? So this is given data, and what we have to prove? We have to prove this upper sum minus lower sum is less than epsilon. So your claim is this UPF minus LPF is less than epsilon. Okay, so the definition of upper integral is now the upper integration over a to b f of x dx, which is the infimum of this UPF so that P is a partition of closed interval AB, and this lower integration over A to B f of x dx, which is a supremum of this all lower sums such that P is a partition of this closed interval AB. These are the definition of this upper integral and lower integral. So by Darboux's theorem, or for any epsilon greater than 0, for any epsilon greater than 0, there exist a partitions P1 and P2 of closed interval AB such that this UP1 F is less than the upper integration over A to B f of x dx plus epsilon by 2, and this lower sum, that is UP2F, P2F is greater than lower integration over A to B f of x dx minus epsilon by 2. Okay. So these are two conditions, but we know that the upper integration and lower integration are equal, and which is equal to the integrations. So we write, what we write? We write this UPF is less than, UP1F than the integration over A to B f of x dx plus epsilon by 2, and this LP2F, which is greater than this integration over A to B f of x dx minus epsilon by 2. So why this is? Because your upper integration over A to B is same as the lower integration over A to B, right? So this is the given data, and we have written this. So now we multiply this by minus sign. Okay, or what we know that instead of taking this, we write also put this P is equal to P1 union with P2, then this P is a common refinement of P1 and P2, right? This is a common refinement. P is a common refinement for this both P1 and P2. So we can write this LP2 F is less than or equal to LP1, sorry, LPF, which is less than or equal to UPF, less than or equal to UP1F. That is, the lower sum with respect to this partition P2 is less than or equal to the lower sum with respect to partition P, and the upper sum with respect to partition P is less than or equal to the upper sum with respect to partition P1. Okay. This is a known condition, right? This is a known condition. Now, now this UPF, which is less than or equal to UP1F, and this UP1F is less than this upper integration over A to B, or instead of taking this integration over A to B, f of x dx plus epsilon by 2. Okay. This LP2, okay, so this LP2 F, which is less than or equal to LPF, and this LP2F is what? LP2F is greater than the integration, lower integration over A to B, or instead of taking this integration over A to B f of x dx. So we will write this as, instead of writing this, we will write this is integration over A to B f of x dx minus epsilon by 2, which is less than, which is less than LP2F, right, and which is less than or equal to LPF, right. This is another condition. We multiply this by minus sign. We will get, this is a minus of integration over A to B f of x dx plus epsilon by 2, which is greater than this minus of LP2F, which is greater than or equal to minus of LPF. This is a third condition. So adding first and two, we get what we get? We get this UPF minus LPF, which is less than this integration over a to b f of x dx plus epsilon by 2 minus integration over a to b f of x dx minus epsilon by 2. Sorry, this is again a plus epsilon by 2. So this implies, or hence UPF minus LPF is less than epsilon, because this integration over a to b f of x dx and minus of this integration over a to b f of x dx will get cancelled, and this epsilon by 2 plus epsilon by 2 will get epsilon. So this is a fourth condition, right? And since epsilon is arbitrary, since epsilon is arbitrary, then okay, this is your aim, right? So we have proved this. Upper sum minus lower sum is less than epsilon. So next is conversely, for any epsilon greater than 0, there exists a partition P of closed interval AB such that this upper sum with respect to partition P minus lower sum with respect to partition P is less than epsilon. What is your claim? Your claim is upper integration over a to b f of x dx, which is equal to lower integration over a to b f of x dx, right? So this is your claim. So we know that this lower sum with respect to p is less than or equal to lower integration over a to b f of x dx, which is less than or equal to upper integration over a to b f of x dx, and which is less than or equal to UPF. This is a known condition, right? So this implies this upper integration over a to b f of x dx, which is less than or equal to UPF. This is a first, this is a this LPF, which is less than or equal to lower integration over a to b f of x dx, right? So this is the fifth condition, and if you multiply these by minus sign, we will get minus of this LPF is greater than or equal to minus of this lower integration over a to b f of x dx. This is the sixth condition. or adding fourth and sixth condition, 6, we get this for integration over a to b f of x dx minus lower integration over a to b f of x dx, which is less than or equal to UPF minus LPF, right? So this is we will get, right? So this is a necessary condition, and we know that this is less than epsilon, right? So this is less than epsilon. It means that this 0 is less than or equal to upper integration over a to b f of x dx minus lower integration over a to b f of x dx, which is less than epsilon. Since epsilon is arbitrary, we will get this integration, upper integration over a to b f of x dx minus lower integration over a to b f of x dx is equal to 0, and hence this upper integration over a to b f of x dx is equal to the lower integration over a to b f of x dx. Thus function is Riemann integrable. Thus f is Riemann integrable. Hence we have proved here. So thank you.